So let's begin again at this slide that shows a 3x2 valve driving a cylinder to extend against the load with a spring retract. Now let's modify that circuit to actually make it so that we can control the retraction speed of that cylinder. How do we do that? Well, so we have the same circuit that we had before, except we actually now have a flow restrictor in the return line to the tank. And this is usually a needle valve, so if you crank the needle valve down, then the orifice through which the fluid has to flow gets smaller and smaller, and that you can control the retraction speed of the cylinder through that methodology. Now we're modifying our circuit, making it a little bit more complicated. We have now a 3x3 valve, so we have 3 envelopes rather than 2. We still have 3 connections. If you look at each envelope, 1, 2, 3, 1, 2, 3, 1, 2, 3. But we have a little bit more complicated valve. Obviously, we have 3 envelopes, and this is a spring-centered valve. So there's a spring on the left and there's a spring on the right, and then there's levers on the left and the right. So if we want to extend the cylinder, we actuate the lever on the left, we push it right, and that makes the leftmost envelope active to extend the cylinder. If we then let go, we go into the blocked position, and then if we move the lever on the right, actuate it, the rightmost envelope becomes active, and that's the retraction envelope for the cylinder. Now normally what will happen, you may have 2 springs, one on each end of the cylinder, but you'll only have 1 lever normally, and if you push it one way, then you extend the cylinder. If you pull it towards you, you will retract the cylinder. If you let it go, the lever will just stick straight up, and the cylinder will be blocked. Okay, I've said this already. So now another thing that happens, we actually have a fairly simple system with this spring retract for the cylinder, but we pay a price for that. What happens is, as the cylinder extends, it pushes against the spring, and when you start out, the spring is not compressed very much. It's compressed very, very little. So the force that you can deliver with your pressure acting over this area is actually pretty high. But the further you push, the more you compress that spring, and of course the spring is the spring force depends upon the spring constant K, and then the deflection X. So the further you push, the greater force you get coming back from the spring. I said this here. So our force that we're delivering out to the load is the pressure times the area of the cylinder, which you'll see in here. But then you have a counter force that's pushing to the left. That's the force of the spring. So you can't deliver the entire pressure force on the piston to the load. You can only deliver part of it because you have to fight against the spring also. Okay. So we have a simple, this is a sort of a guiding principle here. We have a simpler system with our cylinder. It's what's called a single acting cylinder, in that you actuate it only in one direction. But there's less force that you can actually apply with this cylinder because of the spring retract. So you simplified it, but you paid a price for it. Okay, now this is a case where we have a open center, so it's spring-centered, hand lever actuated, 3x4, sorry, valve. In that we have, is it 3x4? Yeah, I think it's 3x4. I always get the number of envelopes and the number of connections mixed up, but We have 3 envelopes and 4 connections. You can count the connections: 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. But the difference here is we actually have a connection between the P port and the T port. So when you are in the locked position, the pump is not blocked, and it can flow. It can send its flow through the valve back to tank. So in this case, at least in this position here, you don't really need a pressure relief because you have a path from the pump output back to the tank. And the way that you write this is we have P connected to T, and then we have A and B, each one alone, blocked. So this is the shorthand designation for that. The cylinder is locked, but the pump is unloaded. Okay? We don't develop pressure, so the pump load is absent. We don't develop pressure here. There'll be a little bit of pressure because you do have channels through which you're flowing back to tank, but it'll be very little. This is also called a tandem center valve. You'll see that designation sometime. One problem with this valve, though, is that all of the flow, when it's in the center position, the default position, all of the pump flow has to go through the open center, and so it could be that you would have to provide a very big internal pathway from P to T for that open center, and that might actually not be practical. The valve would have to be very big. Okay. Now this is another case, a different scenario here, where we have what's called a completely open center valve, spring-centered, hand-actuated, open center valve. Wait, I didn't put everything in there. Spring-centered, hand-actuated, 3x4 open center valve. Okay, so there's a lot of little details you have to put in there. So in this case right here, yeah, in the center position, so assuming, we don't know how it's connected, but this is the, assuming this is the extension envelope and this is a retraction envelope, what we're focusing on here is we're focusing on the center. And so we do have our P connected to our T as before, but the A and the B are also connected there. So what this means is that the port, the cylinder or whatever we're driving with this, it could be a hydraulic motor too, is not locked when you're in the center position. And sometimes you do want it locked, but sometimes you don't. You want it free to move when you're in your default position. It just depends upon the application. So the way we designate this, since all the ports are connected, is you just put P-A-B-T. That means all 3 of them are connected together. And since they're all connected to tank, that means that you have basically 0 or very negligible pressure at every port. Again, you will have some drop between P and T because of the restricted channels through which the fluid's going to flow from the pump back to the tank. But essentially, you're not building any system pressure. The cylinder's not locked and it can move freely. Okay, now what I want to do is give a description here of a valve, just in English, and see if you can figure out what type of valve to draw. So this is a solenoid actuated, spring-centered, 4x3 valve with built-in overpressure protection through a half-open center. Okay, so pause the video and try to draw that. Go through each one of these and try to put it on paper. If you do that, you wind up with this gizmo here. So let's look at each one of them. Solenoid actuated, there it is right there. There's a solenoid there and there's a solenoid there. That indicates that the solenoids can shift it from the center position. The center is the default because of the centering springs shown on the end. So this solenoid can actuate it so that the left-hand envelope is active, and this solenoid can actuate so that the right-hand envelope is active. So if we have this being extension and this being retraction, you actuate this. If you do nothing, then you just have the pump flowing to the tank and the cylinder locked. If you actuate this solenoid, then you extend the cylinder. If you actuate this solenoid, then you retract the cylinder. And this can be characterized, since we have the three envelopes, each envelope has its own connections. And the way this is shown is, since we have a 4x3 valve where we're going to have 4 letters, and then we're going to have 3 groups of connecting these letters together. So in the left-hand envelope, P is connected to A, B is connected to T. In the center envelope, P is connected to T, A and B are separate. And in the right-hand envelope, P is connected to B and A is connected to T. Okay, I want to talk about filters a little bit, but I'm going to stop here and start a new video. So we'll have, I think, 3 in this series.